Astronomy Cast, episode 263 for Monday, April 30th, 2012, Radioactive Decay. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville. Hi, Pamela. How you doing?
I'm doing well. How are you doing, Fraser?
Doing really well. So I wanted to thank everybody who's been giving me lots of feedback on the presentation of the Astronomy Cast app, because people have been finding bugs and more just like tweaks, and I have a lot of control over how I can present the information so it looks as best as you want it on the app itself on your iPhone or iPad. But if you haven't already got it, highly recommend you go and pick up the Astronomy Cast app from the iTunes store. I think it only costs $1.99, $2.99. Yeah. It's not very expensive, and it's got the entire library. You can star your favorite episodes. You can run it on continuous. You can download pretty pictures from it. You can get the descriptions, and I'm happy to keep putting energy into making that app experience better if you guys want to keep giving me feedback. So thanks for letting me know. And then other than that, I think why don't we get rolling?
Okay. That sounds good.
All right, well, here we go then. So, nothing lasts forever, not even atoms. Heavier elements decay into lighter elements, releasing energy as radiation. But thanks to this radiation, astronomers can get a glimpse into what's going on outside and inside distant stars. Let's take a look at the whole process of radioactive decay, the different events that happen, and how humans use this fundamental force of nature for our own nefarious schemes. All right, Pamela, so then when we're talking about radioactive decay, what is the overall process that we're talking about here?
Well, there's a whole variety of different processes, but they all boil down to one concept. You have an atom, it's in a high energy state, and there's something not quite stable about it. And so it gets rid of that instability by releasing energy in some form or another and becoming something new in the process. So it could be as simple as a atom that's at a slightly higher energy configuration that gives off gamma ray radiation and collapses into the same type of atom, but in a slightly different configuration of alignments of spin and things like that. Or it could be something as complicated as it undergoes a decay process that causes it to give off a helium atom, a alpha particle, and it becomes an entirely new type of atom in the process.
But I think it's really important to understand the distinction between radioactive decay of elements and the kinds of reactions that happen between molecules. You know, we can have chemical processes that are giving off energy and recombining atoms together or recombining molecules together, and that's different, right?
Right. So you have atoms bond in a couple of different ways. There's what are called ionic and covalent bonds. Basically, the idea is they either share electrons such that they're filling each other's energy levels, but the electrons belong to one atom, or you have molecules that are formed by electrons that are going back and forth between two atoms and are getting shared. Both of these different types of bonds, they may give off energy in the process of getting torn apart. They may give off energy in the process of coming together. It depends on if it's an exothermic or endothermic. But this is just temperature energy. Occasionally, you'll get flameage. Drop phosphorus into water, flameage occurs. It's awesome. But with radioactive decay, you actually have the atom itself is reconfiguring. And the energy that is given off here, you're getting gamma ray, which is deadly, or you're getting alpha particles, which can be deadly, or you're getting beta decay, again, can be deadly in large amounts. So it's a difference between heat, kind of exciting, or death, which is more than a little exciting.
Right, but I guess to use an analogy, it would be like the equivalent of having a big box of Lego and you're moving the Lego around and making different cars and houses and airplanes and things.
Or your Legos spontaneously become Tinker Toys.
Well, that's exactly it, right? And so at the end of the day, you still got Lego. You know, it's still Lego pieces. You can still recombine them in different ways, but you still, if you had a certain number of little square pieces and little guys, then you'd end up with the same number by the end of it. But as you said, radioactive decay is as if your Lego was actually turning into something else like Tinker Toys. Yeah.
Right.
Yeah. Or like I don't know, glue and pencils and paper or other creative elements. Yeah. So it's it's a completely different situation that's going on. Okay, great. So now I know you sort of hinted at it a bit, but what are the different kinds of radioactive decay that will happen?
So the three primary types of decay are ever so uniquely named alpha decay, beta decay, or alpha radiation, beta decay, and gamma radiation. So it's boring names, but they come from the history. When people first started realizing that there was radioactive decay going on, they had no clue what was happening other than if they took special sensitive glass plates, put them in a drawer wrapped up in black paper, put uranium salt on top of it, and the idea of uranium salt is a little bit terrifying.
It's something that we would all, I mean, how many times have I sprinkled some uranium salt?
And this is where you just have to remember that salts are something that is unique to chemistry and does not refer strictly to food items.
It's going to be one of those episodes, isn't it?
It's going to be one of those episodes. But I finished my salt. I finished my salt statement. So.
Okay, good. All right. Keep going.
Okay, so they realized that when they put this uranium salt on top of this special sensitive glasses, was glass that was treated with various materials, that the glass was getting developed by something. And so they started experimenting, finding different materials that would do this. And as they played, they discovered that in some cases they were able to block the strange rays coming off with just a piece of paper. That's alpha decay. They realized in other cases that in order to block these strange rays that were coming off, they needed something a little bit more substantial, like a sheet of aluminum. That's beta decay. And then they realized in other cases that radiation was just going to blast through just about anything, and lead bricks were required, and that's the gamma radiation. So it all started off with, let's break it down by what's needed to block that radiation.
And then what is actually going on inside the elements themselves? Why are you getting different kinds of radiation coming off of it?
Well, so with alpha decay, you have an atom that's in an unstable configuration where it has more protons and neutrons than it's comfortable with. And so its way of getting out of this high energy state is to literally spit out 2 protons and 2 neutrons, which makes up a helium atom.
Now,
so,
but why does it want more, or why does it have more protons and neutrons than it's comfortable with? I mean, is there some magic number?
Well, it's a matter of atoms have different energy states based on how much stuff is in the nucleus. And the protons are basically getting glued together through different forces that we don't deal with at the macroscopic scale. And as the atoms hit different configurations, it's sort of like when you're building with blocks. If you've ever played Jenga, there's certain energies of the Jenga building blocks that you're like, oh, only having 1 block going across the center, that's not as stable as having 2 blocks going across on the edges. Atoms are kind of the same way. They hit certain configurations where there's just a few too many protons, and it's not as stable a configuration of those building blocks.
And so can you go through sort of waves where you're like, it's unstable, getting worse, and then it gets stable again? And then
exactly.
Right, okay.
And so if you look at there's entire tables of what are called nucleotides. This is the different combinations of protons plus neutrons that make up all the different atoms. And there's all these different valleys of stability as you go up. And so even for smaller atoms, so carbon-14 is an example of this. Carbon-14, it's a perfectly normal atom. You and I both have it in our body, but it's not the most stable of atoms out there, and it would like to collapse to a slightly different energy that's more stable. Okay. And so there's just all these different peaks and valleys of stability and instability. So with certain heavy atoms, atoms that typically have more than 52 protons in them, you have these configurations where it doesn't want to just decay, but it wants to spit out an entire helium atom at a fairly high velocity. And that high velocity helium atom, when it hits you, it imparts a whole lot of energy in a very small distance. And all of that energy getting absorbed by human flesh can be a bad thing. So we prefer not to expose humans to large amounts of alpha particles.
And so, and let's pretend that we did. So let's say you've got some quantity of an unstable element, and you put your hand next to it on it.
Yeah.
You'll get a burn.
You're going to get a burn. You're going to absorb a lot of radioactive materials. And what's bad about this is, depending on how it hits, and this is true of all radiation, is it can actually damage your DNA. And damaged DNA it sort of leads to cancers and things like that. And so a lot of the early research on this, they didn't know they were dealing with something that was dangerous. So Marie Curie, she ended up dying of aplastic anemia, which is believed to have been caused by working with radioactive materials. And the insane part of this is, when they first discovered all of this radioactive material, they started doing crazy stuff with it, making all sorts of elixirs and medicines, not knowing what it did. And so there were all these tonics, these tonics, and they were basically giving people all sorts of radiation poisoning, and it wasn't a good thing.
Okay, so back to our first example. So we've got this situation where you've got a element or a pile of Jenga blocks, and it is unstable, and it wants to kick out exactly a helium.
2 protons, 2 neutrons. Together, no electrons involved. So this is a fully ionized helium atom. Kicks it out, and suddenly you have a new element, and you also have a particle that can do you a little bit of harm. But what's neat is, because they are easy to block, it's fairly safe to deal with these things, and we actually have alpha decay around us all the time. So anyone who has a fire detector in their house, a smoke detector in their house, and everyone listening should have at least 1 and preferably 4 or 5 smoke detectors in their house. Smoke detectors use americium, and I'm sorry if I mispronounced that, americium-241 in the detector. And what the americium does is it ionizes the air in a small gap, and this ionized gap, there's current flowing through it, and when smoke gets into this gap, it breaks off the current, and it's that change in current that causes the smoke detector to go off. Now, it is possible, and there have been cases of kids doing this for science fair, it is possible to gather all of this radioactive material and do bad things, but that requires a whole lot of smoke detectors. So in general, it's not a big deal. There's also alpha decay gets used in radioisotope thermoelectric generators. These are RTGs.
Yeah, and those are for space.
Space RTGs are kind of awesome. They use plutonium-238. Unfortunately, here in the United States, we're out of plutonium-238 for RTGs. So we're hoping Congress will approve the reproduction of this, or turning back on the production lines for this particular radioisotope. But this is another example of alpha decays getting used to generate heat energy and power awesome things, in this case spacecraft.
Right, okay, and then as you said, once that helium atom has been liberated, you've got a completely new element. And this is going back to our Lego box analogy. This is us taking, a little Lego guy and then popping off his head, and now he's actually a wing.
So you have, like, uranium goes to thorium plus helium. So that's one of the common things that we're looking at. So you take an atom, knock it down by 2, you have a new atom. So, all right.
Well, now you predicted 3 types of radioactive decay, and you've only given us 1. So let's hear another one.
So the other type of decay is beta decay, and so here there's actually 2 different types of beta decay: normal beta decay, inverse beta decay. And in both of these cases, you have an atom that is almost stable, but it would rather that one of its protons was a neutron, or vice versa. So protons and neutrons are very, very similar in mass. The major difference between them is protons have a positive charge, neutrons have no charge. So neutrons are actually a more stable configuration for things like really dense stars, but in general, neutrons by themselves, you stick one on a shelf, it very quickly decays into a proton, and it gives off an electron and an anti-electron neutrino in the process. So depending on what you have, one configuration or the other is more stable. It depends on everything added together. Predicting what's going to happen requires many years of quantum mechanics. We're not going to get into that in the 30 minutes of this episode. But at the end of the day, what's kind of awesome is you can have an atom, it's sitting there, it's not quite content, and spontaneously one of its neutrons becomes a proton, and it gives off an electron and an anti-electron neutrino. Or you have an atom that's sitting there being not quite happy, and spontaneously one of its protons becomes a neutron, it gives off a positron and an electron neutrino. So it keeps everything nice and conserved charge-wise, and in the process you end up with a new type of atom again.
But you don't lose, oh that's right, because one of your neutrons is turned into a proton, and so you're actually
right.
going up one.
Or down one, because you can also have, so you can have a neutron that goes to a proton, or you can have a proton that goes to a neutron. It depends on which.
Whatever
it's either a beta minus or a beta plus decay. So inverse beta
right.
decay or a regular beta decay.
Right, but the point being that these, and with the neutrons, I know, you can decay neutrons and you get different versions of the same element, though, right? I mean, you can have
right.
like carbon-14. You're measuring the amount of carbon-14 that's left in a piece of old wood because you're trying to determine how much of it has already decayed.
Exactly.
But it's still carbon. It hasn't turned into...
It's still carbon. So
oxygen.
When you have a proton change into a neutron, then the atom changes identity. When you have a neutron change into a proton, the atom changes identity. So either way, you're going up or down, but with what you're talking about, you simply have a gamma ray given off, in which case the number of protons stays constant. So
whoa, did I just preview the third? Sorry. I'm sorry.
It's
Let's
okay.
go back then.
So,
didn't even say that.
So
we're done.
So with beta decay, so you could have, for instance, cesium-137 goes to barium-137, but you've now changed from having 55 protons to having 56 protons. And in the process, you've given off an electron and you've given off an anti-electron neutrino. So with beta decay, you always have, you're either going up one or going down one, depending on which direction is going on.
But is it always going to want to go in that same way? Is it random that's going to go one way or the other way, or is it will a certain
specific atom will always go one way?
Right. Yeah.
So it's sort of like I'm running out of analogies here. It's really one of these things where it's just like, I'd be happier if you added a Jenga block, or I'd be happier if you removed a Jenga block.
Right. That makes sense. I mean, the best, you can imagine the best strategy from this point on. Yeah. No, absolutely. Okay, so that's our second form of radioactive decay, and then I gave a terrifying preview of the third one. So why don't we just get right into that one then?
So our third state, this is almost always coupled with the beta decay, and this is by far the most deadly form of all of these. And part of the reason it's the most deadly is it's a combination of very high energy and very hard to block. And this is the gamma radiation coming off from gamma decay. So in this case, you have an atom will often decay via one of these beta processes I just talked about. This is where a proton converts to a neutron or a neutron converts to a proton. And the atom that's left behind has an electron that's not entirely in its lowest energy state. So you have or it has the protons inside, they have spins, and so depending on how the spins are aligned, it may not be at the lowest possible energy state. It's close, but not quite there. And so in order to get to the proper energy state, it has to give off a photon of high energy radiation. It has to give off this gamma ray to compensate for the difference in the spins, the difference in the alignments. There's lots of different little things that can change. And when they change, that energy from the change has to go somewhere, and it goes into a high energy bit of light, a high energy photon, a gamma ray photon. So we see this with cobalt, for instance. Cobalt decays, cobalt-60 decays into nickel-60. This is going from 27 protons to 28 protons. And when it's done with this decay process, there's this slight energy difference that it's not happy with, and so it ends up giving off this slight energy difference via a gamma ray.
And let's just be clear on how awful gamma rays are.
They
turn you into the Hulk, as we know. But
well, they turn you into the Hulk, but these are things that just basically blast apart your DNA when they hit it. So a helium atom you can stop with a piece of paper. That's fairly safe. If you spill materials that give off alpha particles, you close glass doors and you pretend it's not there and you put caution tape across this. I kid you not. I've seen this happen in a university laboratory.
Just like, don't touch that over there. Don't,
right,
don't open that door.
Yeah, exactly. It may look like someone spilled chalk, but that gives off alpha particles. Right. With gamma ray radiation, you're looking at brick walls with lead bricks, and still some of them are going to leak through. It's a bad situation. And the gamma rays, they just sort of blast up your DNA, and your DNA doesn't repair itself particularly well, so you're looking at all sorts of different cancers coming from
And so this would be removing our Jenga blocks by exploding them.
Exactly, exactly. You don't want to deal with this.
Don't want to deal with that. Okay, so we've got our 3 methods of radioactive decay, and so then how do we use these in our daily lives? I mean, you mentioned already that we use the decay is it americium?
Americium, yeah.
Americium. In smoke detectors, we've already talked a bit about radioactive decay for carbon dating.
Right. So we end up with radioactive particles get used for a lot of different things. What's kind of awesome is we can actually predict from watching, basically, how long it's going to take for different materials to decay. And so there are a lot of medical applications where you want to treat a tumor with radiation over a prolonged period of time. And so you can do capsules, you can do inserts that they put into the body that have radioactive materials in them with a known half-life, where it's known over this period of time this rate of radiation is going to be given off. It will irradiate the tumor, it will kill off the cancer. That's a good use. Similarly, we can use other forms of radiation for, as we said, for spacecraft radiothermogen RTGs.
Right. And that it's going to be giving off a set amount of energy at a very precise rate that can be then turned into electricity on the spacecraft.
And then we can turn this around, and when we're digging through Earth's soils, we can pull out a rock. We can count up how many atoms of the radioisotope, how many atoms there are of the daughter isotope, the thing that is produced via the radioactive decay, and we can figure out how old that rock is. We can similarly look out at the stars, and we can measure in the spectral lines what the composition of the different atoms in the star is. And so we can start to actually, with extremely long-lived radioactive materials, start to date the stars this way.
Can you give me an example about how they actually will do that? I mean, I know they use uranium, don't they, as one of them? But there's a bunch of different elements. But
there's strontium's another one. There's a whole bunch of different elements, and it's a matter of just changing how many neutrons are inside of an atom changes where the different spectral fingerprint lines are. Very slightly, but if you have a high enough resolution spectrograph, you can see those shifting of the lines. So you can measure how much of each isotope of an atom is in a star if you have a high enough resolution spectrograph. Once you know how much of each isotope is there, you can start to get at the ratios of the amount that's in the star. And that gives you a sense, assuming that all of the material in the star was formed roughly the same time, that can start to give you a sense of what is the minimum age on that star. Now, here on the planet Earth, all of our materials came from supernova. We look at stars. All of these things came from supernova. So we're really saying it's been this long since a supernova went off. And that's kind of cool.
And how long are we saying it has been since a supernova's gone off?
Well, so we know here on the planet Earth, the material that we have was last mixed about 5.5 billion years ago, and then the supernovas are older than that, clearly.
And so this is the situation where you know the rate that the elements are going to be decaying at. You look at a distant star, and you measure those. You call them the daughter elements. You look at the two kinds of elements that should be coming out of this radioactive decay, and then you just measure them. You just compare the ratios, and then you just, I guess, do some math, look up a table, and then just count back and say, oh, okay, we've got 75% uranium and whatever, 25% polonium. I'm just making this up. That tells us that the star is at least 5.2 billion years old. Now, I say the at least part because it can be older than that, right?
Well, right. So this is a matter of mixing, and this is where I say lower limits. So here on the planet Earth, for instance, our stuff that the planet was made from was mixed up at a given point. Now, prior to that, it may have that material clearly existed, but if you had a lump of uranium in the past and it happily decayed, but then it got mixed up later, those daughter elements could have gone off somewhere else. So what you're actually looking at is what is the age that things last got mixed up. And what's kind of awesome is we've observed radioactive decays over 55 orders of magnitude of time. So as precisely as we can measure on short time intervals, as precisely as we can measure on long time intervals, there are decay processes spanning 55 orders of magnitude of time.
So there's just like these overlapping yardsticks that can be used to determine almost anything.
Exactly. And so we can work our way down to the shortest time periods and all the way out to the longest time periods. And it's kind of amazing.
Now, is everything going to decay? I mean, if we go from carbon, 14 to carbon 12, we go from uranium this to uranium that, will we all just end up with protons in the end?
Well, so some atoms we clearly haven't seen decay. There are things that we have that seem to be completely stable. But then we hit this problem known as all the grand unified theories think that protons should decay. Now, we've never seen a proton decay. People have been watching for protons to decay. And the way math works is if you have a probability that one will decay over 10 to the 34 years, if you take 10 to the 34 and put them in a vat, one of them should decay on any given year. And this is how we're able to understand supernovae, for instance. Mm-hmm. We know that any particular spiral galaxy should have one supernova every 100 years. You look at 100 galaxies for 1 year, one of them should have a supernova go off. Same thing works with radioactive decays. Now, no matter how many protons we put in a vat, we aren't seeing them decay. So all the grand unified theories say protons should decay, but we haven't observed this.
But will helium decay?
Well, if protons are going to decay, then yes.
Well, for sure, yes.
but helium seems to be completely on its own, stable in that 2-proton, 2-neutron configuration. It's happy to stay that way. Leave it on a shelf. It stays helium. It stays unbonded. It's inert. Doesn't play well with others. Kind of atom.
Forever. Like it would never. Unless protons decay, right?
Unless those protons decay.
Right, unless its underlying protons are falling apart.
So this is where you get the valleys of stability within the table of nucleotides.
And so, I wonder, what kinds of experiments have been done to search for this proton decay? I mean, 10 to the 34 protons sounds like a lot, but I wonder, is that a lot? Is that as big as a house? How much protons do you need? The big bag of hydrogen?
Well, it's actually a big tank of heavy water is what they use. So you take a big tank of heavy water, and you wait to see if decays take place.
And so the math tells, with these grand unified theories, the math is telling us that a proton decaying is going to release a certain kind of energy. It's going to give a very specific signature, and then you put these detectors all around it, and you wait, and you wait, and they're still waiting.
Nothing.
And they're still waiting. Well, that's weird. Is it like so unusual that it's starting to cause problems with the grand unified theories?
It is.
Really?
It is kind of problematic. And I mean, here's the problem that we have with particle physics right now. We have this standard model that is based purely on observations, that explains the universe we live in fairly well, but doesn't explain the why of the universe that we live in, because it's based on observations, not on first principles. And theorists would love to come up with a theory that allows you to start from math and get to the universe we live in. And we can't figure out how to do that without proton decay. And there's other particles that we're looking for with CERN that if we don't find them, again, we can't get to those first principles. So we're looking for supersymmetric particles. We're looking for the Higgs. It looks like we've probably found the Higgs. But now we're looking for the supersymmetric particles, and without them, we don't have first principles. And we want that underlying math.
Right. Yeah, we've got a whole episode on that, and it's pretty interesting. I don't remember which episode number it is, but yeah, we've got a whole episode where we talk about the grand unified theory and talk about this search for the supersymmetrical particles, and the fact that really this journey of actually finding these things has only really begun. With, if we find the Higgs within the next year, which we kind of probably have.
I think it's just a matter of.
That's not the end of the story. That is really just the beginning.
That's the beginning.
Yeah. Okay, cool. Well, thanks a lot, Pamela. This was great, and I hope this really helped people understand radioactive decay and to not take apart your smoke detector.
And don't eat it.
And don't take any of those exotic tonics and elixirs that contain radioactive spirits.
Sounds like a plan.
All right, we'll talk to you next week, Pamela.
Okay, bye-bye. And stopping my recording, closing my recording so I can gain my computer back. Save. And we'll take your questions in just a moment. We just want to make sure we don't lose the recording. We've only, I think, done that 2 or 3 times in the past several years, but those 2 or 3 times were rather devastating.
Very painful. Yeah. All right. I have saved mine.
Okay, and I'm looking at the comment feed. Yay, we have comments.
And or questions. So feel free to ask us any comments, questions in the questions on Google+, and then we'll get to them. And you can ask questions about this or anything that's based in astronomy, and we'll stick around and answer these questions. Then we'll go sleep some more, I think.
Yeah. Oh, wow. Dasislava Zheleva, I'm so sorry. I know I destroyed that. Has a whole bunch of different questions. So, for instance, and Bridget's been doing a good job at trying to answer. Thank you so much, Bridget. So, for instance, what are the elements with the longest and shortest half-life periods? So the shortest is there's actually some unstable forms of hydrogen. If you take a hydrogen atom and cram 6 neutrons into it, I don't know why you would do this, but should you try for science?
Why would you need to have any reason why not?
Okay, fine, fine. So for science, if you cram all those in for science, then you end up with the shortest half-time that we've measured so far. As for the longest one we've come across is tellurium-128, and it has a half-life of 10 to the 31 seconds. So that's the longest half-life that we know of so far.
That is
that's
quadrillions of years.
Yeah, so that's one of the ones that I think is mostly mathematically, but we do see the child isotopes.
Now, but still, that's not longer than the theoretical half-life of protons.
Of protons, no. So
right.
It could be worse.
Yeah.
And the half-life, it actually comes from, it's a probability thing. So radioactive decay itself is what's called a stochastic process. It randomly goes off, but there's a probability behind it. So if you take a whole bunch of atoms and you stick them on a shelf and you watch them, you can't say when any one is going off, but you can say half of them should go off in this amount of time based on just how unstable they are. So if something's really unstable, it has a shorter half-life.
It's like listening to your popcorn popping. You don't know which kernel is going to go off, but you know that some of them are going to be popping. There's going to be this popping noise.
And there's a fabulous YouTube video that the slow-mo guys did of popcorn going off that I highly recommend finding and watching.
Oh, really?
That
has nothing to do with radioactive decay, but
it has really nothing, cool. But it's really awesome.
So here's another question from Delislava, is what are the predictions of string theory for proton decay?
I don't know specifically for string theory, I have to admit, but in general, all the theories say it should be decaying, and string theory falls into the all of the above say it should decay. So I don't know the specifics, I just know, yes, it's supposed to decay.
So Josh Andrews put in a really great visualization of why the radioactive decay happens. It's this, the valley, the stability. It's very similar actually to the Lagrange points, right? The Lagrange valleys and peaks. You imagine you put your ball up at the top of a mountain, and it will be very stable at that very tippy point. But if it gets
the slightest bit off either direction,
then it starts to accelerate away, and you're off and running. So yeah, that's great. Does Gordon Freeman even know what half-life means? Well, if Gordon Freeman watches this episode of Astronomy Cast, then hopefully that will help. Are there any decay rates at odds with the age of the universe? This comes from Clive Rogers. So that's a good question.
Not that we've found so far. The nice thing is that because it's a stochastic process, all because something has a probability of not decaying for X bazillion years, that doesn't mean it won't decide to do it after half a second. So you can't really end up with a radioactive process that's at odds with the age of the universe. So the way to think of it is if something has a half-life of 5 minutes and you have 500 atoms of it, after 5 minutes, 250 of those should have decayed. But it could be that they all did it within the first half second. It could be that they all waited to the very end. But in reality, they probably just kept gradually going off.
Right. But if you had some like that, what was that element that you mentioned that had a half-life?
Tellurium.
Tellurium. So imagine you had a star or a block of tellurium which was decayed at a ratio that was ridiculous. That would be evidence that the universe was older than we thought.
Or that there had simply been some sort of a unique process that happened right there. It could have gotten bombarded with neutrons. It could have. That's the thing is you can trigger this stuff to happen as well.
Right, but all I'm saying, this is one of the factors that astronomers have used to date the age of the universe, to say.
Yeah, and we haven't seen any.
That's right.
Issues.
We shouldn't see radioactive ratios more than this. And in the stars that we look for, we shouldn't see stars that are older than the universe. And so far, that's what they're finding.
And what's interesting is we have found weird chemical compositions in South Africa, and what it turned out to be was there was actually natural fusion reactions that went off in South Africa where it was just fission reactions. You're right.
Yeah.
Where there was simply this area of uranium that had spontaneous chain reactions occur, and that's kind of awesome that the planet became a nuclear reactor.
And so is it just that you had the right density and the right concentration of material that a natural nuclear reactor took off?
Yes, and that's just awesome.
But there aren't none have been found right now. Like these are
there's none active
reactors,
on the planet.
Ancient ones, yeah.
Yeah.
Wow, that would be amazing.
Oh, your video froze. Let's see if he comes back. I have no clue if you can hear me while I'm talking to his image. If someone could let me know.
So I wonder what would cause that. Like, what would cause that kind of an event to happen? An asteroid strike, smashing a certain amount of radioactive material in, and then it hits so hard that boom, you get a fission reaction.
You're making it far too exciting.
Oh, really?
The reality is, it was just planet Earth. For a whole variety of different reasons, it ends up differentiating itself so that you end up with pockets of hydrogen. Can you still hear me?
Mm-hmm. Yep. I can hear you. You can't hear me? I can hear you.
Okay, now you can hear me. Cool. And I'm somehow in here twice. It's one of those.
I'm going to say that this experiment was probably a failure. I think we're going to go back to the way we do things normally.
So no, you're making it far too exciting. It's our planet as it naturally exists as a way of differentiating itself, so that you end up with pockets of silver, pockets of iron, pockets of uranium, and a pocket of uranium under normal geologic tensions. In one case in South Africa, just underwent spontaneous nuclear reactions.
All right. Well, that is super awesome still. So Maxim Levin asks, can the rate of radioactive decay be changed?
No.
could you? Well, okay. But what if we're firing lasers at it?
Well,
What if we are putting it inside the core of a sun?
so that's not necessarily. You can trigger reactions like if you take an atom and you start bombarding it with neutrons, but that's not a radioactive decay due to spontaneous radioactive decay. That's feeding it neutrons and making it unstable.
What if we cool it down to almost absolute zero? Is that going to have an impact?
I have no idea. I actually, so this is the type of thing where the quantum mechanics get so crazy, I'm not sure how that affects things.
There you go. Crazy quantum mechanics. Okay. So maybe, we don't know. You stumped Pamela. Victory! Okay, so Peter asked a question from last week, which was, could a neutrino pass through the sun without interacting with anything? Could it pass through a neutron star? Could it pass through a neutron star?
Yeah.
Now, what about a black hole?
It would get gravitationally sucked in.
Yeah, and it's not escaping. So neutrinos can't go through light years worth of black holes. They only go in, they don't come back out.
Yes.
Now, who knows what they're doing inside? They might be going through the black hole material, but that's a mystery that we could never look into. Okay, so Carolyn McCardle asks, are there radioactive isotopes that are only man-made and are never found in nature?
Yes. So anything that's particularly, well, okay, let me rephrase that. A supernova can create anything, but if it has a sufficiently short lifetime, we're not going to find it in the wild on the planet Earth, and we have to create it in a laboratory. So there are things that aren't going to be randomly found on the planet Earth, and they will only be found moments after a supernova explosion. Since we luckily don't live moments after a supernova explosion, the only way we're finding those radioactive elements on the planet Earth is to make them in a laboratory.
Now, Owen Roberts has noted that us cloning Pamela is a good thing and not a failure. So the fact that we have more Pamelas briefly should be considered a scientific success. And so perhaps this science experiment was a tremendous success.
Okay.
Good. Well, I think we're all out of questions, so I think we're all out of Astronomy Cast. So why don't we wrap it up? Thank you very much, Pamela. That was wonderful, and we will probably throw another couple of episodes at people randomly. Sorry, that's just what we're doing right now.
Stay tuned to our Twitter feeds and follow us on Google+.
Yeah, and we will be now. Next interesting thing to happen, we're going to do the Weekly Space Hangout tomorrow at 10 a.m. Pacific, 1 p.m. Eastern. And then we're now in summer, so it's like 7, 8-ish, I think, 7 or 8 Greenwich Mean Time. And then we'll be doing our virtual start party, nighttime edition on Sunday night. So not the viewing the sun like we just did yesterday.
And if you want to keep up with everything, follow CosmoQuest X. And sign up for our newsletter. So get an account on cosmoquest.org, sign up in your profile to get the newsletter, and you'll find out when all of these different things are going to occur.
Fantastic. All right. Well, thanks, Pamela. We'll see you later.
See you. Bye-bye.